on the back of my badge, it doesn't have room for the whole name of the panel. It almost looks like it says the Bioethics of Terraforming. So if you're looking for a horror panel, this isn't that. We're going to be talking about the issues of, so what if we go to Mars and find that there is some form of life, very primitive life? What is our obligation, and do we continue to terraform and no way destroy the local ecosystem? And this is a problem which has existed on this planet for many years, and will only get more and more interesting as time goes on. For those of you who were in the Race to the Red Planet panel yesterday, this panel is genetically identical. We have Stanley Robinson on my right, David Levine in the middle, and on the right, Greg Benford, whose twin brother Jim Benford was sitting in the equivalency yesterday.
I got that.
And Greg, I think you have a presentation that you'd like to start with.
Yeah, I thought I would walk through the latest data of the methane impact of the Martian atmosphere, because this is an evolving story, and following on a discovery made about, I think, 3-4 years ago, from first satellite observations, then verified using some telescopes from Earth, and now some further follow-on, more exact stuff with satellite data. And it's not my data, but I will walk through it soon.
No, it's working.
First, this is what we might do. Sorry, but Edgar Rice Burroughs was a tad off. This is not what we're going to be getting, although it gives 1,000 years maybe. It's working intermittently, and just like the methane. The point about the methane is that this is a methane concentration, and you can see that there are areas of the globe which have 5 parts per billion, not parts per billion if you're used to global warming, but per billion. There are some regions, and this is the northern summer on Mars, but some regions have as high as, in the reddish zones, 30 parts per billion of methane. Several points about this. First, it's not everywhere. And the reason it is not smooth and out everywhere, because the circulation time in the Martian atmosphere is in the range of a few weeks to a month, is that this stuff is coming and going very fast. 2 mysteries. Where's it coming from? It seems to be a lot more than you can get geologically. And also, where's it going? Because it's going away faster than the climate models say it should go away. My suspicion is that we may be seeing a reaction with the peroxides in the upper soil, but that's just a guess. The climate people that I've talked to who work on Mars are puzzled. And you know, when you're puzzled in science, that's good news. When you're puzzled by your bank account, it could be bad news. But in science, this is really suggestive of a biological system that is operating better than this. Here's the next. Now, this is the important thing. In regions of such as Asia and so on, those red regions are the most high density of methane. 30, maybe 40 parts per billion. This is seen from orbit. It's detected using molecular absorption and emission. And the interesting thing is, if you overlap that, you find that this is regions where we know there's subsurface hydrogen in case A, they're hydrated minerals in B, B1 they call it, and B2 is volatile substrates, and you'll notice that maps closely to the methane concentration, strongly suggesting there's some reaction occurring having to do with the surface. And these two vary on a scale, time scale of a few weeks. And there, somehow this is all right. So what might it be due to? This is a cold-adapted methanogen, that is, things which eat or produce methane, at the bottom of late. And they've been detected in extremely hostile conditions, very cold, and no oxygen. So we know organisms on this planet that produce methane by using other fuels, for example, H2S. You take H2S plus some carbon compounds and make methane. And in fact, you make methane all the time.
We don't talk about that in the light company.
Yes, call it methane. It's okay. How much water do you need to make the methane that we've seen in the Martian atmosphere? It turns out, I'm just going to read this. You only need 1 part to 6 of maybe what is in the Martian upper surface. That is 1 part per million to make this methane, if it's produced at the reaction rate from those methanogens I showed you in the prior slide. So it's easily done in Martian conditions. You could easily do this. There's no big problem with water budget. We now know there's just lots of water around Mars. So there's some caveats here. I'll let you read those too. I'm one of the persons who believes that most of the audience who attend these talks can read. And these are global estimates. But of course, we observe that the methane generation is occurring locally. So when you do these averages, you're always trying to guess at what really is going on. And but the striking thing with climate people is that the methane is not smooth. It's local. And it comes and goes, much like the weather in Melbourne. So that obviously there's some interesting stuff at work. So these are conclusions, by the way, from my colleague Joe Miller at USC, who's been working on it well. He's looked at the Viking evidence. You may remember that Viking produced a carbon, I think, 14 liquid solution, introduced it into the soil of Mars, and saw that it exhaled a bunch of a carbon compound. Now, that experiment did not distinguish between CO2 and CH4, that's methane, or any other such compound. And if you look at these numbers, these methanogen generation numbers, they are comparable to the numbers that explain the Viking experiment, which is a really interesting, rough numerical coherence.
And we still don't know for sure what caused those ambiguous results from Viking.
And there were odd results from Viking, but they had a time variation that was very, very close to the Martian depth. It went up and down in the Martian depth, suggesting, of course, that it's at least temperature. So, Mars methane producers may exist within the top 10 meters. And we know there's a lot of water around. The interesting thing is, why aren't we seeing some methane out at the poles? Actually, they're going to look at this in more detail soon. But there's obviously plenty of water there. Maybe it's too cold, maybe not, who knows?
Well, the Phoenix lander found some very intriguing, very hospitable environment.
They certainly
didn't actually find signs of life.
Right, so, but to make the counter argument, you can, with using a known geological substance, which is in the Martian regolith, you can produce methane using serpentines. The problem is, it's hard to see how you can do it if it's a geological phenomenon on such a fast time period. I mean, it suggests that either there's some warm flow of fluid that's stimulating this, or something is happening volcanically. But the regions that we see the high methane in are not volcanic regions.
Now, can you explain briefly what a serpentine is?
No. I'm not a geologist. A serpentine is a particular active geological substance, a soil constituent, but it has carbon. So the question is, this is your other slide also, but I promised they might put it up, is many of us feel that massive information, it needs some place to go, or some explanation of why it's spending $19 billion a year. And my feeling is settling the issue of life on Mars. Is it there? And is it like us? And how does it differ from us? After all, it's been there. There's a good argument that, wow, life on Mars is older than ours. At least this is Mars cooled off, at least 100 million years before the Earth. And then there was a lunar incident which reset the clock. Also, we got our moon by collision with Mars like hydrogen. So we would be looking at life, microbial life probably, and a couple of us called Martian races. We do not know what microbes would do if they were left alone and they didn't have to feed with oxygen. So it's a very different kind of life, and therefore, never mind whether you want to do either H2Ls or a Rosborough scenario. This is an interesting example of another kind of biosphere. It's probably the only one we're going to be able to investigate in this century, which will have implications for life throughout the galaxy. Here's another kind of life site that basically started out well and ran out of luck because our system's small, couldn't hold on to its atmosphere to dry out and cool down. So this is a basic science question we can solve. I personally don't think we can do it with robots at all, and neither, by the way, does the planning board of NASA, because I was on a board some years ago that tried to look at how we would investigate this problem robotically, and the people at Carnegie Mellon said, sure, we can design a robot that could go down in caves we know exist on Mars, we don't know, or we could drill repeatedly to depths of tens of meters, but we won't be able to deliver it until sometime after 2040. My feeling is there may not be a space program with it up in budget by 2040 the way things are going.
And if we can send something that would present some interesting results, interesting to the public,
yes,
then that would excite people and that would keep the budget going.
That's
I mean, it's kind of a self-perpetuating thing. I think a lot of the science fiction fans would like to see NASA going, and if NASA does something interesting, then it'll get more money and do more interesting things. If it continues on this sort of research and development track like it has for the past 20 years, not so much. Now, my philosophy is a little bit different. I think that in the grand spirit of human exploration, we see that out there in the distance is a life form that is different from ours, and therefore it is our duty to go and wipe it out. It's what we've done for hundreds of years. I don't see any reason to stop now. But seriously, okay, I'd like to take the discussion from the realm of science into the realm of science fiction, if I may. Let's just posit that all of this data pans out in the most positive possible way. Let's just say that we go to Mars and we find that there are life forms different from our own, life forms that are just barely existing in the extremely harsh environment. And we've come there, and it's now hundreds or maybe even thousands of years later, and we are establishing a presence on Mars that's sufficient to actually say, we should spread out from these domed cities or what have you. We need to take control of the surface, express our manifest destiny, or take off population pressure, or whatever. We need to change the climate of the planet to make it hospitable to our own form of life, and that would almost certainly mean wiping out a Mars-adapted form of life.
Actually, it doesn't have to. I mean, when I go under the surface, don't give a damn about our atmosphere. After all, they're methanogens. A meter down beneath the soil of Melbourne. I mean, we haven't wiped those out.
Despite our best efforts.
No, actually, we just didn't know about it. I mean, we're not responsible for the action. It came here over a billion years ago.
So that's part of the bioethics of terraforming is maybe we can make the planet Mars hospitable to our own form of life without negatively affecting the life that's there.
But it's quite possible. But more to the point, this is actually not the realm of ethics. Ethics depend upon social relations. We don't have social relations with microbes. In fact, you've all been killing microbes this morning. I mean, if you brush your teeth, you're killing microbes. I mean, you don't owe something to methanogens.
But wouldn't you say that bioethics includes our effect on the ecosystem broadly stated, which obviously includes far more plants and microorganisms than things with faces? I mean, the thing is, it's our ethics. And I mean, I think when we talk about bioethics and whether or not we have a right to negatively impact the biosphere, of course the question is, what impact does that have on human beings in the end?